All right, everyone. So yes, once again, I would like to welcome you all to the next thematic session 2. That's going to be all about sustainable energy and energy storage. But before I invite our chair, I would like to tell you all that as this networking can seed SEO member state collaboration for possible cross-border R&D projects in science, technology, and innovations, and all the queries of the upcoming talks can be sent to the chat room, which will be addressed by respective speakers at the same time. So make sure you're making the part in. Also, that particular moment, if there is any delay or any interruption in the PPT, our team would be waiting for 30 seconds. And in case if it's not ready, even though, then we shall proceed with the next presenter as per the schedule. So moving on to the forum side, our next thematic session 2 is all about sustainable energy and energy storage. And I would like to invite our chair, Professor BK Panigrahi and Dr. Anil Kumar. But just to notify you all, Dr. Anil Kumar is not available due to some medical emergency. So Professor BK Panigrahi is going to take over the forum side. Welcome, sir.
Yeah. So good afternoon to all of you. I hope I am audible.
So you have to be a little bit more louder.
Yeah. Okay. Is it audible? Everybody is able to listen to me?
Yes, sir. Absolutely. Yeah.
Okay. So thank you for the introduction. So again, I beg apology. My co-partner, Dr. Anil Kumar, is not well. So I'll share my presentation and we'll discuss about this sustainable energy and storage thing. Okay. So good afternoon to everyone. So I extend a hearty welcome to all the participants. I'm thankful to the organizer giving me the opportunity to chair the session and deliver 15 minutes about this thematic area, that is sustainable energy and storage. So I'll stick to the time of 15 minutes. I'll end by 4:20. This is 4:04 now. So if you look, my topic I have chosen today is smart, sustainable, secure, and self-filling grid. So that is S4G. Being a power engineer, I am giving the emphasis on the grid perspective, because when we are talking of the sustainable energy and when we are talking of the storage at large, so the main point to be considered here, all these renewable energy sources are to be integrated ultimately into the grid. So what exactly we want to share here, I don't know, just the slides are not moving. Just a second. I hope this mode is better. So this second slide I'm going, because if you look into this in Indian scenario, we are committed to reduce the GHG emission up to 33 to 35% by 2030, whatever we are in 2005 level. And similarly, we have set a target here to produce 30% of non-fossil based electricity generation. So when we are looking into the renewable energy sources, we have to add more and more renewable energy in the form of solar, in the form of wind, in the form of small hydro, biomass, etc. So the most important thing is, generally in India, if you are looking into, we are rely upon on the solar and wind. So while talking about the solar energy and wind energy, so either it is in the off-grid mode or it is to be the grid-tied mode. So when it is off-grid mode, for example, any domestic solar, rooftop solar, that is simply a beautiful example of the off-grid. Or it may happen that we are considering a off-grid taking into certain number of houses in a locality where there is no grid available, no electricity available. So we can have a small cluster, okay, of the generation that is either solar or biomass. So all are to be integrated in a clustered manner and they can feed power to a small locality. So nothing to do with the grid. But the importance of all these renewable energy generation is gradually increasing, and it poses a challenge when we are incorporating all these power production in a larger extent to the grid. So you can look into the here the major challenge is in the case of this solar and wind generation, that is the variability and the uncertainty. Because the variability means the solar insolation level varies. It depends on the intensity of the solar insolation. So the main important thing is, if you are looking into this slide, the major challenge is the variability of the solar generation. And the second challenge is also the uncertainty, because we are not able to predict accurately how much will be the solar and how much will be the wind power. So this poses a great challenge whenever we are having a grid where the generation are coming from different sources, renewable as well as the non-renewable. Because the generation from the fossil fuel plant, that is thermal power station, that is fixed, nuclear power station, that is fixed, we can control it. But generally, we don't have the control and the amount of generation of the power from the solar and wind, because as it is dependent on certain factors like the solar insolation and the wind speed. So the major challenge which we are facing is basically with the increase in the penetration of this renewable energy, and in particular nowadays also every government is giving emphasis on the increase in the penetration of the electric vehicle. So you can thought these electric vehicles is also one of the energy source. Either it can work as a sink or it can work as a source. Whenever you are charging your battery in an electric vehicle, so it becomes a sink. You are taking the power from the grid. But if you have enough power, you can discharge also to the grid. So that's why this is basically a dynamic storage. So what exactly I am driving out is it is very good. We can make our grid green. It is very good. We can make our entire power production clean. So to get this green and clean power, we have to integrate more and more renewable generations, solar, wind, etc. But this poses a challenge. Why it is a challenge? Already I have mentioned to you, because if it is a grid tied, then the question is these, because of the uncertainty in generation, because of certain other factors, technical factors, which we'll discuss, the grid poses a main challenge. Now, to avoid those uncertainty, the variability in the generation, either I have to support these generations with a storage backup. So all these renewable power generation from the solar and wind are either having a storage backup or it is without having a storage backup. So this variability can be mitigated by this particular storage. So the main idea, please go to the next slide. So in this next slide, to achieve this target, what exactly we can do? Can we give some facility to the renewable energy generators so that they can be encouraged to participate in power generation and supplying to the power, and simultaneously they can help my grid to increase the grid stability. So the impact, we have to study very categorically the impact of all this generation in the grid, the impact of all the storage, because if you are looking into the storage, there are different type of storage. I'm happy to see the presentation of the young scientists. Many of them are working in new storage technology. You may develop a new storage type of solar cell. You may develop a new type of battery. The battery material, you can use nanomaterial for enhancing the performance. So that is another area of research. So that's why you can have the storage in the form of electrochemical storage, thermal storage in the mean of heat pump, mechanical storage by flywheel, electromagnetic storage by supercapacitor. So every storage is having its own characteristics. Okay, but we are looking into what is the impact into the grid. Hence, I can just make a summary here. Our grid needs expansion because as our power demand is going on increasing, it needs an upgradation, but simultaneously, all the challenges posed by the integration of the renewable energy and storage needs the adaptation of new technology, that is the smart grid technology, for a secure and reliable operation of the grid. So when I'm taking this, in that case, we have to study this grid integration. We have to look into the system operator, the independent system operator in a power plant, that is ISO, and simultaneously we have to look into the investor, those who are investing into the local power production by means of the solar park, by means of a wind park. So a effective grid integration of this renewable energy and storage, it can be achieved if it is multifarious. We can have a proper planning. We can address the interconnection issue. Therefore, there are certain grid codes have been developed in different parts of the country. Europeans are having their own grid code. India is having their own grid code. So everybody is having their own grid code. It tells about the strategy of integration of this renewable into the grid so that your grid becomes a robust grid. It should not lose its stability. So we want a flexible and secure operation of our grid. So the smart grid technology which we are focusing upon, that is the flexibility service from distributed generation. So we are coming up with a prosumer driven approach. Suppose I have a solar rooftop solar in my home, and in a society we are talking of now smart building. In a smart building you have solar generation of your own. Either you can consume your own power, but if you have the surplus amount of the power, you can sell it to the grid so that during the peak hour of the generation, the grid impact you can tolerate to some extent. So that is generally we call a local power balancing. We do a demand response. So the consumer as well as the producer. So if I have a solar rooftop solar, I act as a prosumer. I am a consumer, I am a producer, but when I have to produce, when I have to consume, this should be balanced by some policy, by some incentive. Otherwise, I won't go for that. So that's why the new smart grid technology, even if in India, we are now planning to propose or implement the demand response. And similarly, the storage is another choice. For example, if you cannot deliver, you have excess energy. So you are producing more amount of the solar energy in the daytime, but all my appliances are not used during that particular time. So I'm talking of a single home. If there are thousands of home, hundreds of home together in a cluster, so now it is a concept of a microgrid. We can frame our autonomous microgrid so that my power can be used by my neighbor. So similarly, you require some storage at that time. So the storage at home, individual home, all these storage at different home can act as a large storage to be integrated into the grid. So a flexible operation, a flexible control, as well as a flexible protection strategy is needed for that. So that's why these are the grid scale battery energy system. We can support the LV grid, MV grid, and extra high voltage grid. We can support the data center. The most power consumption generally we do the diesel power, the power we are taking from the diesel. One is the railway, after that the telecom towers. A lot of telecom tower, all they run on the diesel generator because for the networking and others. So we can have this there, the use of the battery. All my young researchers, they can come up with the idea. For example, the vehicle, we are using a battery in the vehicle. So that is a dynamic storage. The storage is not fixed. It is moving from one point to the other. So electric vehicle are completely changing the loading pattern. So now suppose a battery which is not suitable for the electric vehicle, can I use it for the static purpose? Like any other purpose I have mentioned, for rural electrification, for a data center, for a telecom tower. So you have to work on the material, reusability of this battery, disposal of this battery. So that is most important aspect nowadays you have to look into. So there are various battery technology. All the work has to be done in this various battery technology, looking into its application. Does it require a static application? Does it require a dynamic application? Whether it is a cell level manufacturing, whether it is a cell or it is a pack. So these are the some area where you have to think upon the research should carried on this. So that's why this is India's first grid scale utilization in Delhi. So where the main idea of this storage is multifold. You can have demand response, power quality, the reserve, you can provide the reserve, etc. I'm not going into the detail of this particular one. The next aspect which I'm looking into, this is an overview of the smart energy system. The main idea is how effectively you can integrate the various energy vector. When I'm talking of the energy vector, either it is a battery storage, or it is PV, or it is wind storage, or it is a large vehicle parking lot which can dispose to that. So now the whole system is subjected to a lot of variation of the energy. How effectively you can utilize all this energy. So that comes a planning problem. The AI ML plays a very important role here, how all this energy can be shared with each other. So we require an autonomous operation of all these. looking into the grid condition so that it can support the voltage, it can support the frequency. So the most important thing, how this storage, how this PV generation can take part in ancillary services. Ancillary services means they can support the service of the grid, they can support the voltage, they can support the frequency. So large scale battery storage and EV to participate in the frequency regulation, which is mandatory for the grid. There comes your grid code. All the available energy source must provide ancillary service. We have to look into the interconnection standard. So these are the some smart grid technology where it purely depends on the modern control, the modern communication technology, as well as a proper planning also. So we need optimization, we need planning, we need control, we need protection. So now this is a multifarious domain. So all the engineers, whether they are a power engineer, communication engineer, telecom engineer, or you may be the computer science engineer, you may be data analyst or data science, they play a major important role in the smart grid scenario. So no longer it is confined to the power. And again, I am giving all these are interdisciplinary in nature. Let us join together to achieve the goal of the smart grid mission, to achieve the goal of the solar mission, to achieve the goal which our Prime Minister is always proposing, the Atmanirbhar Bharat. We have to develop our own standard. We have to develop our own tools, techniques, methodology. So that is important. This. So lastly, this is a local energy system which is mostly useful for us because India, you know, that is having a lot number of rural villages where power has to be reached. So there you can have solar, there you can have wind, there you can produce biomass. Then so these are the generation vectors. So similarly, there are consumers. The consumer may be for heating. You use electricity for heating, for cooling, for transport purpose, for battery operated system, and the electricity for common use. So how to have a coordinated approach between the generation and the demand. So always the generation and demand should be balanced. If the generation is less, demand is more, can I have a demand side management? Can I reduce mine? So that's why this is a complete picture to have a control architecture for optimized utilization of the availability of the energy, as well as a self-dependency, self-sufficiency. Just yesterday, I got an article from IEEE magazine. They in USA, they have developed an autonomous microgrid having cluster of 60 or 70 homes. So you try to reduce your dependency on the grid. You have your own generation, you can have your own load, then you share your load most effectively so that the generation and load can be matched. So there are two things what I will discuss. Either it is an autonomous microgrid where there is no grid, or you can interface it to the grid and have a balance so that your dependency on the grid can be reduced. So this requires, this is one of the standard recently developed in India, particularly for the interconnection of this renewable and how this ancillary service can be achieved by these energy sources. So these are some electrical parameter, how to maintain the voltage, how to control the frequency, how they can take part in different ancillary services. I'm not going into the detail of that. So these are the standard. So that's why my sincere request to the young researchers, they are also encouraged to look into these standards. The standards may vary from country to country because looking into your, but at least the range of the voltage which you can tolerate, the frequency which you can tolerate, it can be decided by regulatory commissions. Okay, so that's why finally this is a microgrid. We can work in this microgrid having a lot of communication technology. So once you are having the communication technology, the challenge is the cyber security. So cyber security is must in the smart grid scenario. The cyber security is must particularly to protect this critical infrastructure. So that is another aspect of the research domain in this particular area. Right. So these are the challenge which already I have put to you. And thank you. I'm just concluding my talk because the time is I've just crossed this time by 2-3 minutes. So basically, my emphasis here is various research domain which can be incorporated into an existing grid. So the research can be done in any part. Either it is a material development, it may be a solar cell material, it may be a fuel cell material, it may be anything, it may be the heat energy production, local energy support. So there, my sincere request is there are various vectors of the power generation So these vectors of the power generation have to be efficient simultaneously. Why we are generating it? It has to be integrated to the grid. So we have to look into also the grid condition. We have to support the grid rather than, because all these generation are power electronic generation, which make pollution to the grid. Pollution in the sense the injection of harmonic and other things. So we have to avoid that. So that is the main thrust research area. So last line, this research is interdisciplinary research. So we have to join together to do this particular interdisciplinary research and do something in this energy sector or storage sector. It is not an individual research. So that's why all the idea which will be gathered today, we'll take it as a challenge. We'll try to solve different challenges. Thank you for listening. If you have any questions, we can take.
Any questions? I guess so. You have made it like supremely clear for everybody altogether. Well, thank you so much for being with us. It means a lot to us. Thank you.
Thank you.
And I think here we are moving to take a part into young scientists' presentations. And moving further, I would like to call Vivi Liu from Yunnan Academy of Scientific and Technical Information, China, to please take over the forum virtually.
Oh. Can everybody hear me?
Yes.
Okay, so I'll just go ahead and share my screen. Okay, so good afternoon and good evening, everyone. My today's sharing is about the exploration of mechanism for developing sustainable energy in SCO countries, and I am Wei from China. The reason why I want to sharing this topic is because we found some challenges when we want to developing the sustainable energy, especially in the developing countries. Although we know the energy crisis we all face can be relieved by using the sustainable energy, and the most of these products involves the technology transfer process. But we found that in most developing countries, including the SCO countries, the market and the transfer mechanism is far from being well developed because the lack of pathways and channels to transfer technologies and also the lack of professional technology transfer institutions. And when we want to introduce some advanced technologies into developing market, we found those technologies are sometimes are too advanced to their absorptive capacity. And that makes the technologies and the products are not always closely related to the market demands, and the technology lacks a strong sense of service after being transferred. So, and the second phenomenon is the market does not always accept or they are willing to replace the traditional energy resources with a sustainable energy. And the two phenomenon combines, but not enough economic benefits from the operation to the host firms. And so that's why we need to realize that introducing sustainable energy to some new developing countries is not just a process of capital equipment supply from one to another, but also includes the transfer of skills and know-how for operating and maintaining technology hardware and knowledge for understanding this technology so that the further independent innovation is possible made by the receptor countries. And we also need to realize that different stakeholders shall be involved, such as the government, the private sectors, the research institutions, IP protections institutions, so on and so forth. And we have some practice and exploration on helping the sustainable energy developing. For example, we build collaborative platforms. Some active platforms, for example, the China South Asia Technology Transfer Center, which is the STDC, helps the sustainable energy developing in countries such as India, Pakistan, Afghanistan, etc. And we also organize the seminars and workshops, and we also help to build the demonstration sites in countries such as India, Pakistan, and some other ASEAN countries. And we help to build the regional network. For example, we have collaborated with ASEAN Secretariat and the United Nations Asia Pacific Technology Transfer Center to build the Asia Pacific New and Renewable Energy Technology Transfer Base, which aims to introduce technologies and products from developed countries. And we also help the Chinese companies to build a joint venture with partners in Thailand, and has very good products. Even in the first year, it established in Thailand in 2015. And therefore, because of the like nearly decades of working, we have summarized some approaches when we want to developing the sustainable energy. First is to apply support from the government, including the policy guidance and financial support. The economic development of SEO countries varies greatly from each other. So it is very important to seek government guidance on political and economic and social respects of your target countries. And sometimes the financial support from the government can be very important as well. And you can apply for like a project grants from the government and to get some financial support. And the second is to establish channels and to develop understanding about each other, you and your possible partners through activities like the forum, like matchmaking event, seminar communication, so on and so forth. And so the channels and collaborative platforms between the relevant companies and markets can be built. And three is to conduct a survey on the market demand and of your target country and select the applicable technology products. Uh, the market research, market survey are quite important in deciding whether the technology can be successfully popularized in your target country, because the information about the economic condition, the current situation, and possible issues and various needs of the recipient countries market can be obtained as realized not all good technologies and products are suitable to be introduced. So that's why we need to go through the market information you need. And number four is to build demonstration sites and projects. It is help the society to have a practical contact and practical understand of the new energy technologies or products, because we need to realize like sustainable energy products or the technology itself is not very common knowledge to the whole society. It's not like the mug, you go to the supermarket and you just buy it and you know how to use it. And the market and the community need to have some time to learn and to adapt to the new technology, and they need to learn the benefits the new technology can bring to them. And number five is to seek solid input from the government, including the political support, the financial support, and also the support on training and personal exchange. The political support can bring some continuous or like solid economic income. For example, we have such solar PV water pumping system in the rural area of China, and we negotiate with the local government and finalize a so-called a feeding mechanism to the project company by giving their authority to collect the money from the users when they want to use the water from the project, and it helps the company have continuous economic benefits from the project, and at the same time the households, they have benefits from using the from this project, and they are willing to maintain the operation of the project, so gives the project continuity. And also the personnel training and exchange is very important as well, because the receptor firms can truly understand the technology, or at least the skills to maintain the operation of the projects. So it's not necessary for the host firms to send technicians or personnel to go to the place and solve the problem or help the maintaining all the time, and save cost for both parties. And number six is the set up the joint venture in the receptor country, and helps companies to explore the foreign market and commercialize the energy solution products, and also help the capacity building of the new joint venture, and also help to facilitate the commercialization with a lower cost. And here are some parties that we think may involved in this whole process. We can see like that there are like more than one, sometimes more than one technology transfer institutions can be involved as a bridge to link up the host country with the host firms and the receptor countries or the receiver firms. So it is very important to have such a network to help you to save the cost and to minimize the risk. And here are some advices on future cooperation we would like to have with SAO countries. First is to build a mechanism of high-level cooperation and policy dialogue. It is mainly between the governments of countries. And it's better if we can have, for example, the ministerial level dialogue mechanism to popularize the sustainable energy products. And second is to build a multi-channel investment risk mechanism. And sometimes the government fund is not sufficient enough for each projects. So like social funds can be also included. For example, the low interest rate loan, the venture capital, the angel funds, so on and so forth, can be also included. Number three is to complete the incentive policy for technology innovation commercialization. And for example, the feed-in tariffs is very good one to encourage investors to build the sustainable energy projects. And the fourth is the joint R&D activities, including for example, the joint laboratories or the joint R&D R&D activities between two countries, between two organizations, to test and to get the data on the new sustainable energy technologies. And the number five is to enhance the technology demonstration and promotion. And it is game to give the community more chance to know how good your energy or your products are, and give them time to realize it before you really enter into the market and commercialize your products. And last but not least, I would like to speak a little bit about the organization I work for, the YASTI, Yunnan Academy of Scientific and Technical Information. And we actually do a lot of research on technical service, S&T cooperation and climate change, so on and so forth. We have certain international platforms that we can provide a very broad network, and we also have some friends in the South and Southeast Asian countries and organizations. And thank you very much for listening, and should you have any questions, and please contact me directly, and thank you all.
All right, thank you so much, ma'am. I guess you have made it supremely clear. We don't have any question queries. Thank you so much. Well, here we'll be moving to the next presentation, everyone. So the next presentation is by Li He Socho University, China. But due to network issue, he requested to play his video presentation. So here we'll be presenting his video that's going to be webcasted right now.
Ladies and gentlemen, nice to meet you here. I'm very glad to share my research with you. My name is Le He, and I came from Suzhou University, which is located in the beautiful city of Suzhou. Before joining Suzhou University, I obtained my PhD degree from the University of California, Riverside in 2013. Then I worked as a postdoc at the University of Toronto. The title of my talk today is the design of nanostructured materials for photocatalytic carbon dioxide hydrogenation. First of all, let me briefly introduce the motivation of our research. So today, we are living in a world facing many global challenges, such as the coronavirus pandemic, climate change, energy shortage, and environmental pollution. The demand for clean and renewable energy has been ever increasing day by day. In this context, photocatalytic CO2 hydrogenation is a process to utilize the solar energy for the conversion of greenhouse gas CO2 and renewable hydrogen into fuels and feedstock chemicals. I guess most of you have heard of the concept of hydrogen economy, which is to use hydrogen as a medium for the conversion and storage of renewable energy. However, we simply cannot power everything with hydrogen. By combining hydrogen economy with CO2 economy, we will have more freedom to use renewable energy. For example, we do not need to replace our cars with electrical ones if the fuels are now made from hydrogen, CO2, and renewable energy. While this idea looks very nice, the problem is that the solar to chemical energy conversion efficiency is still quite low, and practical applications of this technology is not feasible right now. To improve the energy conversion efficiency, a new photocatalytic pathway was recently developed based on the photothermal effect of nanostructured catalyst. In this process, the catalyst is locally heated to a high temperature by the sunlight and then drives the thermocatalytic reactions. This photothermocatalytic pathway can utilize much more photons from the sunlight, essentially across the entire solar spectrum. However, the photothermal properties and catalytic performance has to be balanced in existing photothermal materials, and these two parameters are key factors affecting the efficiency. My group has made great effort in the development of catalysts with enhanced photothermal catalytic properties. We have been trying to improve the photothermal property of materials without sacrificing their catalytic performance. Here, I just want to show you one example of our catalyst, which can maximize the absorption of sunlight and thus increase the photocatalytic efficiency by 20 times. I have to point out that there's still plenty of room for further improving the energy conversion efficiency of photothermal CO2 hydrogenation processes. Along this direction, we will design catalysts with both excellent photothermal and catalytic performance by breaking the limitations of existing materials. By doing that, we hope to achieve a 5% efficiency of solar to chemical energy conversion in the near future, which is compatible with that of natural photosynthesis. To make our dream come true, it is necessary to find collaborators from different areas. First of all, besides materials, the design of a photocatalytic reactor is also very important to increase the energy conversion efficiency. Experienced chemical engineers are more than welcome to help us to design better reactors. Second, we are also looking for collaborative studies on the mechanism of photothermal catalysis. The knowledge on the mechanism is very useful to provide a guideline on how to design better materials. We are particularly looking for experts on the simulation of catalytic processes. Moreover, if we would like to transfer this technology into markets in the future, techno-economic analysis of photothermal catalytic systems would be a key step, which may need the expertise from the chemical industry. As a materials chemist myself, I wish to find partners within the SCO countries to develop new CO2 economy. Finally, I would like to take this opportunity to welcome everyone to visit our city and our university after the pandemic. Suzhou is a very beautiful city. It is very close to Shanghai. It just takes 30 minutes by the high-speed train to travel between Suzhou and Shanghai. The ranking of material science and nanotechnology at Suzhou University has raised dramatically during the past decade. For example, 10 years ago, we were over 500 in the ranking of material science, but now we are moving to 39. So we are very open to international cooperation, particularly within the SCO countries. That's pretty much for my talk today. Thank you all for listening. I'll be happy to take any questions and suggestions. Thank you. Ladies and gentlemen, nice to meet you here. I'm very glad to share my research with you. My name is Le He, and I came from Suzhou University, which is located in the beautiful city of Suzhou. Before joining Suzhou University, I obtained my PhD degree from the University of California, Riverside in 2013. Then I worked as a postdoc at the University of Toronto. The title of my talk today is the design of nanostructured materials for photocatalytic carbon dioxide hydrogenation. First of all, let me briefly introduce the motivation of our research. So today, we are living in a world facing many global challenges, such as the coronavirus pandemic, climate change, energy shortage, and environmental pollution. The demand for clean and renewable energy has been ever increasing day by day. In this context, photocatalytic CO2 hydrogenation is a process to utilize the solar energy for the conversion of greenhouse gas CO2 and renewable hydrogen into fuels and feedstock chemicals. I guess most of you have heard of the concept of hydrogen economy, which is to use hydrogen as a medium for the conversion and storage of renewable energy. However, we simply cannot power everything with hydrogen. By combining hydrogen economy with CO2 economy, we will have more freedom to use renewable energy. For example, we do not need to replace our cars with electrical ones if the fuels are now made from hydrogen, CO2, and renewable energy. While this idea looks very nice, the problem is that the solar to chemical energy conversion efficiency is still quite low, and practical applications of this technology is not feasible right now. To improve the energy conversion efficiency, a new photocatalytic pathway was recently developed based on the photothermal effect of nanostructured catalyst. In this process, the catalyst is locally heated to a high temperature by the sunlight and then drives the thermocatalytic reactions. This photothermal-catalytic pathway can utilize much more photons from the sunlight, essentially across the entire solar spectrum. However, the photothermal properties and catalytic performance has to be balanced in existing photothermal materials, and these two parameters are key factors affecting the efficiency. My group has made great effort in the development of catalysts with enhanced photothermal catalytic properties. We have been trying to improve the photothermal property of materials without sacrificing their catalytic performance. Here, I just want to show you one example of our catalyst, which can maximize the absorption of sunlight and thus increase the photocatalytic efficiency by 20 times. I have to point out that there's still plenty of room for further improving the energy conversion efficiency of photothermal CO2 hydrogenation processes. Along this direction, we will design catalysts with both excellent photothermal and catalytic performance by breaking the limitations of existing materials. By doing that, we hope to achieve a 5% efficiency of solar to chemical energy conversion in the near future, which is comparable with that of natural photosynthesis. To make our dream come true, it is necessary to find collaborators from different areas. First of all, besides materials, the design of a photocatalytic reactor is also very important to increase the energy conversion efficiency. Experienced chemical engineers are more than welcome to help us to design better reactors. Second, we are also looking for collaborative studies on the mechanism of photothermal catalysis. The knowledge on the mechanism is very useful to provide a guideline on how to design better materials. We are particularly looking for experts on the simulation of catalytic processes. Moreover, if we would like to transfer this technology into markets in the future, techno-economic analysis of photothermal catalytic systems would be a key step, which may need the expertise from the chemical industry. As a materials chemist myself, I wish to find partners within the SCO countries to develop new CO2 economy. Finally, I would like to take this opportunity to welcome everyone to visit our city and our university after the pandemic. Suzhou is a very beautiful city. It is very close to Shanghai. It just takes 30 minutes by the high-speed train to travel between Suzhou and Shanghai. The ranking of material science and nanotechnology at Suzhou University has raised dramatically during the past decade. For example, 10 years ago, we were over 500 in the ranking of material science, but now we're moving to 39. So we're very open to international cooperation, particularly within the SCO countries. That's pretty much for my talk today. Thank you all for listening. I'll be happy to take any questions and suggestions. Thank you. Ladies and gentlemen, nice to meet you here. I'm very glad.
Thank you so much, sir. Well, here we'll be moving to the next presentation by young scientist. And here I would like to welcome Heping Lee from College of Information and Communication, National University of Defense Technology, China.
Hello everyone, it's my great pleasure to give a presentation in next 10 minutes. My name is Haipeng Li, and I am from the College of Information and Communication, National University of Defense Technology. The topic of my presentation is Ambient Electromagnetic Energy Harvesting and Backscatter Communication. We will explore the novel methods for the realization of a new generation of IoT, short for Internet of Things, with high spectral efficiency, no energy consumption, and no maintenance. In recent research, our group used rectified metal surface to collect and reuse the ambient EM energy, which is short for electromagnetic energy, and also use the digital metal surface to communicate on basis of ambient carrier waves. These two methods make the completely passive sensor nodes possible. So at first, I want to give a brief introduction to the metamaterials and the metasurfaces. Metamaterials are artificial materials that doesn't exist in the nature. They are usually consist of artificially constructed subwavelength unit cells, and they have specific features such as a negative refractive index. And the surface is a kind of two-dimensional materials. It's fabricated by placing the quasi-periodic elements on the surface of the dielectric. It can flexibly control the phase, amplitude, polarization of the EM waves. In recent years, our research group has used the surface to realize high-gain antenna, electromagnetic energy convergence, and force-based multifunctional beams. Now back to the topic of our report, which is also the current interest area of our group. In today's world, IoT technology is being integrated into all aspects of our life and has been widely used in smart cities, smart homes, smart agriculture, logistic monitoring, and wearable devices. With the advent of the 5th generation era, people have put forward a beautiful vision of the Internet of Everything, but the Internet of Everything is facing many problems that need to be solved, such as the scarcity of spectral resources, high energy consumption, and serious environmental pollution. So how to solve this problem? We know that while resources in the energy and the EM spectrum are scarce, there is a surplus of resources in our surroundings, such as the digital television and video signals, Wi-Fi signals, and Sentinel signals. They are valuable ambient EM signals. How to use them to solve the problems of the power supply and communications problems? has become a hot topic. I think this topic at least include two issues. One is to harvest and reuse the ambient EM energy. We call it open source. And another issue is to use the ambient waves as communication carriers for energy conservation. We call this flow control. So for the ambient EM energy harvesting, the traditional method is to use a rectifier antenna to convert the radio frequency energy to direct current and then store it. But in our group, we achieved the conversion from the radio frequency to direct current by loading the PIN diodes directly on the strong currents at the mat surface. We compared the CSR evaluation board of the PowerCast ink with the rectifying mat surface we have designed. By recording the charging time at the same distance and power, as the results show that the new method can harvest energy almost twice as fast as the traditional one. Meanwhile, we can design rectifying mat surfaces of different size to fit various signals and achieve a good cascade. And we can also design flexible control structures for easy confirmation to arbitrary platforms. In addition, when the EM energy in the environment is too weak, we can use this kind of focusing mat surface to concentrate the energy and then collect it more efficiently. After EM energy harvesting, let's talk about more energy efficient way to communicate. That is ambient backscatter communication. It's a kind of passive communication way by using the ambient signals as carrier waves. The conventional method is to control the motion of the antenna to modulate the information at the scattering wave. For the novel method, we use digital mat surface to modulate information. When the PIN diodes on the mat surface are turned on, the input waves will be reflected, and we can regard this state as state 1. And when the PIN diodes on the surface are turned off, the input waves will be transmitted, and we can regard this state as state 0. By controlling the states of the PIN diodes, the information can be modulated at the scattering waves easily. Here are the traditional and the new ambient backscatter communication system built by our group. The left picture is the traditional one, the right is a new one. The new system has a communication distance over 50 meters. In summary, our research will provide new methods for the realization of a new generation of IoT with high spectral efficiency, no energy consumption, and no maintenance. So in the future, we can conduct extensive collaborative research in many areas, such as the intelligent agriculture environment monitoring, and the intelligent building control, and wearable body information sensing, and smart home. In related fields, we have already worked with the research group led by the Professor Probert at the Indian Institute of Technology. So far, we have an invited paper in IEEE ISWC 2019, and we also have a collaborative paper in IEEE OJCOMS. As a result show, our method can achieve better transmission reliability with the same spectral sharing factor. And that's all of my report. Thanks for your listening.
Thank you so much, sir. Well, here we'll be moving to the next presentation. And to make a part Dana, may I request Shravanti Sudhendra Joshi from JS Mandal Marathwada Institute of Technology, Aurangabad, India, to please take over the forum. Over to you, ma'am.
Yes, so I would like to make sure that I'm audible as well as my screens are visible.
Yeah, everything is perfect. Please go ahead.
Okay, good evening everyone. I, Dr. Shravanti Joshi, extend my warm greetings to distinguished Professor B.K. Panigrahi, esteemed senior scientist and young scientists present at the conclave. As observed from the past few decades, excessive CO2 emissions by human activities has dramatically changed our ecosystem. This makes it imperative to find methods that can mitigate CO2 emissions and to as well as replace an increasing portion of fossil fuel by renewable sources to meet current global energy demand. In this context, extraordinary class of perovskite materials are attracting great deal of attention. These perovskite materials are ternary and quaternary compounds constituted of earth-abundant elements and have suitably positioned band gaps for CO2 photoreduction. These perovskites are also adaptable to band gap engineering, which further enables them to harvest greater fraction of photons in terrestrial sunlight. For the current session, I'll be focusing on my group's activity on tailored synthesis of perovskite for CO2 conversion to value-added fuels in gaseous form such as carbon monoxide, methane, and hydrogen gas. Now, the major novelty of the work lies in our concentrated efforts to formulate perovskite-based solar ink and its integration on an insulating surfaces like glass to lower the production cost during prototype commercialization. In the past, we were focused on developing chemical routes for synthesis of hierarchical nanomaterials for application as brake and monitor devices. These devices developed consisted of multifunctional sensor arrays that were capable of degrading organic dyes in UV as well as visible light. Also, they were capable to simultaneously monitor CO2 gas evolving as a byproduct in presence of 10 to 15 cross-interfering gases. Now, in a way, the work done during this doctoral period laid foundation to ongoing research activities at Functional Material Laboratory. Moving on, calcium titanate with a basic chemical formula AbO3 has a distorted perovskite structure and is an incipient ferroelectric and diamagnetic material. In first of its kind, exotic calcium titanate nano architectures were synthesized using solvothermal method with tailored facets and in situ self-doping mechanism. Now here if you see X-ray diffractogram reveal high crystallinity and orthorhombic crystal structure. Further, if you see the FESM images, you can realize good quality tailored facets. Further, here we did not use any co-catalyst and still managed to achieve better CO2 conversion rate as illustrated by this image. As for the conclusion of the study, among all the nanostructures synthesized, only hierarchical spheres gave us good photo reduction capabilities. Further, under UV light, 3 times more fuel-based products were produced, whereas under visible light, we were able to achieve 8 times the capacity. Now, this is when compared to standard anodized titanium dioxide. Based on this encouraging results, uh, we further developed a different chemical strategy wherein we used high symmetry epitaxially grown tubular calcium titanate nanostructures for photocatalytic CO2 reduction. A careful observation of XRD and TEM studies reveal fast stacking interplay of triple one planes confers rectangular shape with orthorhombic crystal structure. Now here if you see compared to the doping which we have used, that is silver, iron, and chromium. With silver nanoparticles, we managed to get a very good photocatalytic CO2 conversion rates. Further, the three-dimensional nano-architect structure enabled more light harvesting activity. Here, the metallic dopants used did not alter the crystal structure, but on positive side, if you see, they enhance the optical absorption by fine-tuning the band gap. Although the results were exceptional, but these results are only good from publication point of view. If we see commercialization plans, few drawbacks such as difficulty in forming good quality thin films as well as photo corrosion really hindered our plans for commercialization. Again, we were back to zero position, and at this point, we really pondered over many materials, and search led us to organic inorganic halide perovskite. Now, these perovskites are very promising in solar cell application. Their sudden increase in popularity was observed when organic inorganic halide perovskite solar cells, they showed improvement in power conversion efficiency from an initial value of 3.8% as reported by Kojima et al. To 22% in matter of just 6 years. In wake of such remarkable performances, few demerits such as high sensitivity to humidity, oxygen, heat, as well as low stability restricted their use. Now, inspired by these drawbacks, in 2015, Kovalenko et al. For first time they reported on an all inorganic halide perovskite comprising of cesium, lead, chlorine, and bromine. Now, in addition to overcoming the previously mentioned issues, the inorganic halide perovskite in the report showed many excellent properties as listed here, thus hinting at a class of exceptional nanomaterials for CO2 conversion. In recent time, Kwang et al. And Zhu et al. Reported on cesium, lead, bromine, quantum dots for photocatalytic CO2 reduction. In both the reports, exceptional results were mentioned. But if we look very closely, lead toxicity and lower service life further restricts the commercialization plan. Now, inspired by such scope, through our ongoing DST project, we plan to overcome these issues by developing lead-free inorganic halide perovskite-based cost-effective devices. Currently, we are focused on developing portable devices integrated with solar ink based on such perovskite nanocrystals. The work is being done in collaboration with Aston University UK and Greaves Cotton Limited India. Now, recent trials gave us good results in terms of highly monodispersed spherical morphology using green chemistry routes. Further, we were able to form single crystal thick films on glass substrate and effectively reduce CO2 gas to value-added products. As per our trials, we are very confident that the solar ink technology that we are developing in our lab has full potential for adoption from commercial point of view for green fuel production. We are currently working towards two main outcomes in terms of improved process conversion efficiency as well as grams scale synthesis. Scientific collaborations for us are opportunity to engage in collegiality and let credibility and validity to our research activities. We are actively engaged with many overseas universities in terms of knowledge transfer, development and fabrication of prototypes for energy generation, chemical sensors, and medical diagnostics. Currently, we are having Dr. Wiley, who is a collaborator through DST project. A few months back, we had also collaborated with Professor Tamara from Tom State University, Russia. We also welcome partnership in mutually research mutually interested research areas, and more specifically in carbon neutral technologies, environmental remediation. Um, our strength again is also in chemical sensors and medical diagnostics. At MIT Group of Institute, we have a wide range of basic science and technology-based activities going on. For starters, we have Functional Materials Laboratory, which is a DST-sponsored lab fully equipped to carry out research in the areas of nanomaterials, engineering, chemical sensors, heterogeneous catalysis. Then we have MIT CARS. Again, this is related to agricultural activities, soil testing, and so on. Then we have rapid prototyping and plastic processing training centers. Again, automation and robotics center as part of advanced CAD/CAM CAE learning. We have also in the past done a few biodiesel related projects as well as solar power plant projects. Moving on, currently we are having BIREX sponsored MedTech lab and incubation center. Again, MIT SIP, which is industry relevant micro enterprise dealing with plastic processing. Then we also have Center for Advanced Material Research. Basically, it houses all high-end instruments for characterization. Again, we have ARDC, which is related to agricultural activities. Currently, we are in collaboration with Israel and other overseas universities this ARDC has. With this, I would like to end my talk. Thank you.
Thanks so much, ma'am. All right, ladies and gentlemen, so here we'll be moving to the next presentation, and to have a part done, may I request Saurav Chandrakant Batankar, Institute of Chemical Technology, Mumbai, India, to please take over the forum.
I hope you can see the screen and I'm audible.
Yes, yes, we can.
Okay. Hello everyone, I am Dr. Saurabh Patankar. I am currently joining from the east coast of India. I am happy to share my perspectives on utilization of one of the largest available natural resource, which is the agricultural waste, and how it fits into the overall scenario of the sustainable energy. So climate change is threatening to alter the socio-economic fiber in agrarian countries. Rainfall variability makes it difficult to predict agricultural yields, making it the farming community apprehensive. The temporal pollution issues due to crop residue burning also adversely affects this farming community. There is a need, therefore, to develop new technologies that will utilize the agricultural waste and generate steady revenue stream for the farming community and insulate them from the detrimental effects of climate change. Agricultural waste is a renewable resource, and using it makes sense from the sustainability viewpoint. My work has been focused on developing new catalytic technologies to convert agricultural waste into functional polymers and high value phenolic chemicals. So one of the high value functional polymer that can be made from biomass is nanocellulose. Now, nanocellulose has a tensile strength like steel. It can be used to make transparent films that have excellent gas barrier properties, and thus it has wide ranging applications. Now this molecule 2266 tetramethyl piperidonyl 1-oxyl, or TEMPO, which is the trade name for it, it is a classical oxidation catalyst which has been used traditionally to regioselectively oxidize the primary hydroxyl groups on cellulose fibers, and thereby enabling the disintegration of fibers to make nanocellulose. However, this molecule is toxic to aquatic life, and it cannot be let into drains very easily. Like you cannot, there are issues with sustainability while handling this particular catalyst. And so, however, if we ensure that tempo is anchored to a support that can be taken out easily from the reaction mixture, then the nanocellulose production can be made sustainable. I found out that cellulose fibers have pores up to 80 nanometers on their surface at certain moisture content. So I decided to anchor this tempo on some anchors or nanoparticles which can penetrate the cellulose fibers through the pores on its surface, oxidize the hydroxyl groups on cellulose, and then can come out of the come out of those pores from the fibers and can be isolated easily without letting tempo into the drains. I chose to anchor this tempo on iron oxide nanoparticles that can be easily separated at the end of the reaction using a magnetic force. However, iron oxide is susceptible to change in its oxidation state due to the reaction conditions like high pH, the redox environment, etc. So I coated these nanoparticles in silica or glass and then covalently anchored tempo by consecutive selenization and reductive amination steps. I was able to synthesize nanocellulose with the same properties as the one made from usual homogeneous or free tempo process. Even the rate of reaction with hindered tempo due to the anchoring of it on nanoparticles was similar to the free tempo reaction rate, albeit at a very, slightly higher temperature. We further used this sustainable nanocellulose, which was made using this new heterogeneous catalyst to make these tubes, which can further be used for some biomedical applications. Now, moving into my current research and the way forward, I strongly kind of believe that measuring is knowing. And I developed a metric called V factor to estimate the profitability of biomass valorization processes, considering the factors like capital expenditure, the operational expenditure, process yields, resource availability, price fluctuations, tonnage of manufacturing, etc. And it has been a realization through that exercise that unless sustainability is the only goal, it is not profitable to make only energy from biomass. Like if we focus only on the energy point, it really becomes difficult to compete with the traditional fossil fuels, which are way cheaper in the current scenario than the energy derived from biomass. And so biomass is a polymer with a unique combination of carbon, hydrogen, oxygen, and it makes it suitable to make functional polymers with only slight modifications. So depolymerization of biomass can yield chemicals that are typically made by isolating and oxidizing the hydrocarbons. Thus, biomass is best suited to make high-value petrochemical analogs and novel high-performance materials. For example, lightweight, moisture-resistant textiles can be made profitably from biomass. Now, I'm currently working with a startup company on producing virgin cellulose pulp fibers, uh, vanillin and oxidized polymeric lignin from the agricultural waste. The biomass is first fractionated into cellulose, hemicellulose, and lignin fractions by using a benign organosol process, followed by the oxidative depolymerization of lignin to yield vanillin. Now, vanillin is a platform molecule owing to the multiple functional groups on it, and apart from its utility as a flavoring agent that fetches good revenue. The oxidized polymeric lignin has carboxylic groups on it and an altered glass transition temperature that makes it easier for fusing with other virgin polymers. It can therefore be used as a filler in packaging and textile industries. So the point which I want to make here is that unless we use biomass for high value applications, using some of it for sustainable energy really is challenging from the economics point of view. Continuing this work on making high value chemicals from agricultural waste, I focused on this step of making vanillin from the lignin. So I tested the efficacy of the oxidative depolymerization of lignin using the same anchored tempo catalyst. Now this catalyst has free amine groups on it on which the tempo is anchored. And so I thought that these amine groups might be able to give the basic sites which are essential to abstract the protons from lignin and then start the oxidative depolymerization using the redox sites which are given by this tempo. The traditional oxidative depolymerization of lignin is done in an alkaline environment, and the process results in around 700 kg of alkali waste per kg of vanillin isolated. And so I was able to do this reaction at neutral pH using hypochlorite as an oxidant, primary oxidant. And I was able to get around 20% yield of vanillin and associated compounds, high value phenolic monomers from kraft lignin. However, the vanillin yield varies with the lignin type, and I'm currently exploring the variations in order to develop a robust process. An interesting aspect in therefore the cost-effective biomass valorization process development is this using such multifunctional catalyst that can be used as a divergent technology, targeting many feedstocks rather than developing unique technologies for targeted products. So instead of developing one technology for one particular targeted product, developing a technology that can harness uh, the functionality in multiple feedstocks and can result in multiple products is what is needed in biomass valorization uh, in order to make it economical. Uh, Biomass valorization will also be profitable when all these bottlenecks in it, like pre-treatment, the fractionation, catalytic conversion, and subsequent purification is made cost effective and efficient. I have developed and working over a catalog of catalytic processes for producing value-added chemicals from biomass. After fractionation of biomass, cellulose component is suited for making aliphatic chemicals, as you can see here, whereas the lignin component is most suited for making phenolic chemicals. So investigating structure activity relationship in materials and designing new catalysts for each of the plausible pathway in this catalog is one of my ongoing activities. So I have divided my work on biomass valorization in three broad categories and seek collaboration with the SCO member states in these three domains. The first is focused on the feedstock procurement and management, as identifying the quality and quantity of biomass produced with change in seasons is critical. The second is on the catalytic process development, wherein the novel reactor systems have to be used for biomass valorization, where new reaction mediums like the solid reactions, where the catalyst is the solid phase as well as the substrate is in the solid phase. So these systems like these have to be used in biomass valorization, and so therefore I have to explore this use of novel reactor systems for the one part fractionation and modification. When we use these new systems of solid reactions, there is no mathematical framework available for this to model these systems and extrapolate the results for unknown process conditions. And so I also want to work in this area of developing mathematical framework for this solid catalyst solid biopolymer interaction reactions. The third area is on finding new applications for valorization products, as many of these valorization products which we can get from biomass do not have existing petroleum analogs. So we do not know the applications of these products. And based on the structure activity relationships, based on the properties of those materials, we have to explore new applications for such materials. Now, finally, talking about little about my institute. Uh, my Institute of Chemical Technology was established in October 1933, and it works with intention of advancing India's knowledge reserves in chemical science and technology. The institute has grown to become a premier university devoted to education, training, research, and industrial collaboration in chemical engineering, chemical technology, applied chemistry, pharmacy, biotechnology, and bioprocessing. Institute of Chemical Technology has been ranked among top 10 engineering institutes of India. Finally, I would like to thank the Department of Science and Technology, India, and Indian Institute of Chemical Technology, Hyderabad, to give me an opportunity to present my work in Shanghai Cooperation Organization Young Scientist Conclave. I also would like to thank all the scientists and delegates for your time and attention. I would be happy to answer any questions with respect to my work. Thank you.
Thank you so much, sir. Well, ladies and gentlemen, here we'll be moving to the next session, and that's by Jada Shankar Osman University, Hyderabad, India. But as he's not available over here technically, so Dr. Jada Shankar could not join and requested us to play a video as he's busy with his PhD final PPT. So yes, before we make the proceeding part, many, many congratulations to him. And here we'll be playing the video from his side.
Good morning, everyone. I'm Jada Shankar, Department of Physics, Usman University, India. I am going to talk on synthesis and characterization of rare earth and transition metal doped perovskites for multiferric applications under the theme of sustainable energy and energy storage. My work experience related to this talk is ACR1-X FeXO3, where A is NdVdEr perovskite nanoparticles were prepared by Solar autocombustion technique. Crystalline size of these samples found to be in the order of 20 to 50 nanometers. Most of these samples exhibited gain dielectric behavior in the order of 10 to the power 3 at room temperature. All these samples except ER-FeO3 perovskite showed weak ferromagnetic behavior. ER-FeO3 perovskite exhibited ferromagnetic behavior. Empty plots of NdCr1-X FeXO3 perovskite system were carried out under up to 300 Kelvin at 0.01 Tesla and 0.5 Tesla fields. Empty curve of x is equal 0 and x is equal 0.3 sample at 0.01 Tesla field exhibited novel magnetic diamagnetic-like behavior. With further increase in temperature, Fe content reversal magnetization is disappeared. NdCrO3 perovskite showed relaxer ferroelectric behavior between 178 degrees centigrade at 100 Hz to 225 degrees centigrade at 1 MHz. These materials are useful for capacitor, superconductor, multiferrite, and energy storage device applications. Introduction to innovative idea. In the multiferrites, coupling between the electric and magnetic polarizations enables the magnetoelectric effect. Dielectric constant, magnetodielectric, and magnetoelectric coupling of Bi 0.4, Pr 0.03, Lu 0.03, FeO3 perovskite at room temperature is found to be 250 and 2.3 percentage and 1.2 millivolt per centimeter Oyster respectively. Dielectric constant and magnetoelectric coupling of Pb Fe 0.5 Nb 0.5 O3 perovskite at room temperature is found to be 1.4 into 10 to the power 3 and 400 millivolts per centimeter Oyster respectively. Magnetization of LaFeO3 bulk and thin film perovskites are found to be 0.44 EME per gram and 60 EME per gram respectively. Remanent polarization of NdFeO3 bulk and thin film perovskites are found to be 0.01 for microcoulomb per square centimeter and 5 microcoulomb per square centimeter respectively. Activation energy of mobility of charge carriers of LaFeO3 bulk and thin film perovskites are found to be 0.20 electron volt and 0.96 electron volt respectively. These results found to be thin film or alternative for future generation of multiferrite applications. Also, it is noticed that high dielectric and magnetic materials possess significant magnetodielectric coupling. These possibilities are sparked me to design multiferrite device application devices. Innovative idea. Preparation of bulk and thin film perovskites of LaFe1-X MnXO3 and LuFe1-X MnXO3 and Lu1-X LaX FeO3 and La1-X LaX MnXO3 perovskite compounds. Study the XRD and SEM and IDAX structural properties. Study the optical photocatalytic activity and photoluminescence properties. Study the magnetic, dielectric, and magnetoelectric coupling and magnetodielectric PE, pH, IV, and olefin properties. To develop methods for understanding and estimation of properties of different materials. Understand the origin of ferroelectricity, ferromagnetism to found the multiferrous coagulation in the system. Understand the properties of the materials to identify the commercial and industrial applications. Investigate and propose at least one multiferrous device for practical applications. Approach. Solely auto combustion method is used to synthesis bulk ferrous material. Spin coating method is used to synthesis in filling ferrous material. Optimize the rare and transition metal doping in required ratios. Structural, morphological, electrical, magnetic, and multiferrous properties to be carried out for optimized samples. Expected outcomes. LaFe 1 minus X MnXO3 and LuFe 1 minus X MnXO3 and Lu 1 minus X LaX FeXO3 and Lu 1 minus X LaX MnXO3 perovskite systems of bulk and thin films. Compounds have to be prepared for a wide range of applications such as multiferroids, transformer cores, motor, spintronics, magnetoelectric switching, and energy storage device applications. Possible collaborations with SEO nations and area of interest. Many collaborations possible with SEO nations, basically from Russia and China. At present situation, all countries are suffering from economic crisis due to the COVID-19 pandemic situation. Once everything is clear, I am sure that I can get collaboration with SEO nations. I am interested in multiferrous, thin films, gas sensing materials, batteries, glassy materials. About the institution and country. Usman University is the oldest university in India, established in the year of 1918, which is located in Hyderabad. India is the thousands years of old with rich culture and religious diversity with 23 official languages. Thank you for and all.
Thank you so much, sir. And now, ladies and gentlemen, we'll be moving to the next session. And here we have a Corbo Alexander from Federal Research Center for Chemical Physics, named after NN Semnov, RAS, Russia.
So, hello, everyone. So I'm starting my presentation right now. So can you see my slides? Hello?
No, sir.
Oh, one second. And now?
Not yet, sir. Yeah.
Okay, great. Okay, so hello everyone again. My name is Alexander Skavlevov. I'm a leading scientist at Federal Research Center for Chemical Physics. And my research is devoted to catalysis and transformation of small molecules. And today I will present you some of our recent results and achievements on activation of nitrous oxide. So first of all, why we are interested in this topic. So nowadays, nitrous oxide gained significant attention, first of all, due to its environmental effects. It was found that it is the dominant ozone-depleting substance emitted in the 21st century, and also it is a potent greenhouse gas, so it has approximately 300 times greater warming potential than the CO2. And most of anthropogenic emissions of nitrous oxide, they come from agriculture and the chemical industry, and the latter emissions, so the emissions which come from the chemical industry, free, so the emissions on which we can influence somehow. They're currently just destroyed by the thermal decomposition into elements, into nitrogen and oxygen. By the way, India produces a lot of waste natural gas. And obviously, instead of just decomposing nitrous oxide, it would be much better to do something useful with it, so to find some application for this byproduct. And we believe that nitrous oxide is a promising reagent, and one can outline two main directions for developing the chemistry of nitrous oxide. So for decades, people tried to exploit its high oxidation potential, tried to use it as a powerful oxidizing agent and oxygen atom transfer agent. And the second direction, which is much less explored, and I think which is much more interesting, is utilization of nitrous oxide as a building block for the construction of more complex organic molecules. So we worked on both of these directions, and here is a small summary of what we've done. I will very briefly mention our most noticeable achievements. We found that some of the ruthenium complexes, highly labile ruthenium alkene complexes, they're capable of activating this highly inert nitrous oxide molecule. So we even managed to establish some of the products, so primarily products of the reaction catalysts with N2O. And these ruthenium systems, they are able to efficiently promote oxygen atom transfer from various substrates to various substrates. So basically to oxidize them. So also we found that inert reagents, so very basic and relatively cheap organometallic compounds, they also react with highly inert nitrous oxide, resulting in the formation of hydrazines, which are useful and containing compounds. And probably fundamentally most interesting our finding is that antihypercyclic carbenes, so free carbenes, they are able to fix nitrous oxide at very mild conditions, at room temperature and at normal pressures. So they fix into with high yields, no special requirements are needed. And further, we found that these adducts could be easily converted into isoimidazolium dyes with high yields very efficiently. And these isoimidazolium dyes are industrially important, very applied dyes. So we patented this method also. And overall, our results demonstrate that nitrous oxide is a useful reagent, not just a byproduct industrial gas. And it could be used for the creation of more complex products. So it's not necessary to just compose it. So here is a vision of our work, what we do. The molecules like dioxygen, dinitrogen, hydrogen, CO2, N2O, and methane are small, and some of them are very inert, like N2O and methane, and also CO2, but they're very impactful. So they're critical players in potential future energy cycles. Several of them, so they play a key role in the climate change and other environment important issues. And because they are involved in elementary reactions relevant to the efficient and reversible storage of energy and release of energy from their chemical bonds, they're integral to all technological scenarios for post-fossil future energy systems and for potential more stable society. And as a consequence, massive efforts are being devoted to converting those small molecules to high-value chemical feedstock and fuels. And mastering the chemistry of these molecules represents a prime challenge of our century. Our efforts are currently put into the search of efficient catalysts and photocatalysts for efficient small molecules activation and synthesis on the basis of high-value chemical feedstocks. These are possible areas in which we can collaborate. So other scientists of our organization, of my group, for example, so I'm interested in organic chemistry in general and catalysis, photo-induced transformations, fluorescent and photochromic materials, and especially in hydrocarbon H-aliphatic stage activation. So briefly about our institute. Our institute, I'm working in the Simonov Federal Research Center for Chemical Physics. It's named after Nikolai Simonov, who won a Nobel Prize in Chemistry in 1956. And so in the areas in which our institute actually works is organometallic chemistry and catalysis, photochemistry and femtochemistry. So we're also interested in fundamental principles of polymerization processes and structure and properties of new polymers, and also we're interested in physics and chemistry of combustion and shock waves and detonation. So with this, I would like to finish. Thank you very much for your attention.
Thank you so much, sir. Well, here we'll be moving to the next presentation. But before we move the proceeding part done, as we are going to be visualizing the video over here rather than he being virtually available. So yes, may I now request Menshevok Leah Institute of Physical Chemistry and Electrochemistry, named after A.N. Frunkman, RAS, Russia, to please have the declaration part done by the video presenting over here. Okay, so
good afternoon.
Yes, please go ahead.
Good afternoon. Yeah, thank you for kind introduction. My name is Ilya Menshikov, and today I will speak about new solid-state adsorption storage systems of methane and hydrogen storage based on nanoporous composite materials for energy applications. It's well known that natural gas or methane and the hydrogen are the most promising fuels of future because they meet all modern requirements in the field of clean energy. However, we use these types of fuels in gaseous supercritical state, and we can't compare their energy bulk density, for example, with gasoline or diesel. That's why we have to apply different technologies for their storage and transportation, such as compression, liquefaction, or pipeline gas infrastructure. Nevertheless, all these methods, all these technology possess critical disadvantages, such as high pressures, high energy cost of refueling, expensive cryogenic tanks for LNG, enormous ecological load, and so on. That's why we have to find new alternatives which can which can be in the future the most promising for gas industry in common. So adsorbed natural gas or gas in common in adsorbed state is a quite promising technology, and it is based on the physical phenomenon methods of adsorption, which uses special porous materials with very precise porous structure, which can adsorb gas molecules. And you can imagine this process just how the sponge adsorbs water. And this, you can see on this picture, the system without adsorbent and with adsorbents. Yellow balls is the models of the gas, and this is the porous structure of this material. So we can use this technology for improvements of this for gas storage and transportation. On the right side of the slide, you can see comparison, for example, of this system of adsorbed natural gas, which uses special material carbon adsorbent, with simply compressed gas. And we can see that at 5 megapascal, for example, we can achieve twofold beneficial storage capacity in comparison with CNG. And also, these are technological features and positive outcomes. So, for example, reduction pressure of inside the system leads to improvement of energy efficiency. Increased gas storage capacity of these systems compared with compressed natural gas will extend refueling interval and low energy consumption. And which is very important, the thing is, which is very important is that these systems are more safe in comparison with common because the gas molecules are kept in a bound state inside the adsorbent. So, of course, the key element of these systems is a special nanoporous materials. If we speak, for example, about natural gas or methane storage and transportation, we have to use nanoporous carbon-based materials and composites, carbon-based composites. So in our group, we have a very good experience in this field, and we design special materials for adsorbed natural gas storage systems. Of course, we prepared special route for their preparation. First of all, we simulate adsorption processes and determine the desired properties of real material. After that, we select appropriate precursor and appropriate synthesis conditions. And after that, we prepare the material and we correct all its designs and its states after each test because we have to prepare an ideal material for gas storage. And here you can see the results of our research, carbon-based materials for adsorbed natural gas storage with advanced storage capacity and flexibility, high adsorption cyclic stability, mechanical strength, and high packing density. And these are composite carbon-based material, which uses also metallo-organic framework structure. And on the right side of the slide, you can also see the comparison of adsorbed natural gas system storage capacity with compressed gas. And you can see, for example, at 5 megapascal and in temperature 273 Kelvin, we can achieve 5-fold advantage in storage capacity in comparison with CNG, which is higher than 200 cubic meters of gas per cubic meters of the system. If we speak about hydrogen storage and transportation, so we need other type of materials. And the MOF-based functional materials are the most appropriate because we can adjust their structure and porosity parameters, just changing the metals and organic linkers. But the main disadvantages of these materials are their low density, low stability, and low mechanical strength, especially in initial powder state. So in our group, we develop special technologies for shaping and functionalization of these materials, and we can produce such kind of pellets, tablets, and granular metal organic frameworks. We can be used in the systems, for example, for small energy applications such as drones, robotics, and other types of small power resources. And these materials have desired properties and special precise porous structure, advanced operational properties, mechanical strength and stability, and readiness for small batch laboratory production. So it's necessary to highlight that gas storage in adsorbed state can be used in the all range of gas consumers, from on-board system for vehicular applications and household facilities for example, heat and electricity, up to very high capacity strategic gas storages with gas inside them, up to several cubic meters of millions of cubic meters of gas. So we can cover all the fields of gas storage consuming, which is very important. And now I will show you recent results in this field with comprehensive results and devices. So using prepared materials allows us to prepare a new generation of the natural gas storage systems for vehicles. You can see the pictures of the systems which can be easily mounted in the automobiles. You can see the storage system, for example, with cylinder, which filled with the adsorption material, and which is very important, low operating pressures provided the possibility to optimize the design of gas tank and move from awkward cylinder to ergonomic flat adsorbent as this one. So it is very important. We can lower pressure, we can improve the energy efficiency, and we don't need more to cover useful place inside and space inside the vehicle for these awkward systems. So we can finally use this flat panel. And this is a parameters of such kind of systems. Also, they have fire explosion safety, high energy efficiency, and ergonomics and design. This is very important, but these systems are more safe than, for example, in comparison with CNG or liquefied natural gas. And on this slide, you can see the first in the world gas terminal adsorption gas terminal for gasification of remote consumers or small settlements where it is impossible, for example, to make pipeline gas infrastructure. So for outside, it looks like a cubic container, but inside you can see its cell structure, which is occupied by blocks of carbon materials. This system has fire explosion safety, energy efficiency, ergonomics of design. It has in the volume of 10 cubic meters, it works at 70 bars. It can carry on more than 20 hundreds of cubic meters of gas. And it's very important thing that this system has the dimensions of 10 feet container and can be transported by any kind of transport to the consumer. And afterwards, we can use gas for electricity, heat, and so on. And the really important thing that our technology, for example, for adsorb, if we consider adsorbed natural gas, is the simplest one and is the cheapest one. So we don't need any facilities for charge or discharge of our system, for example, as for CNG or LNG. And also we have no any gas losses during its using and its operation. And that's why we can decrease the cost of the gas, which is much more lower in comparison with that for the CNG system or LNG system. And this is very important thing, and it is the main positive economical outcome from our technology. So several words about our institution. Our institution is the leading scientific center with almost 1,000 professionals. It was established in 1929. We are experts in adsorption, corrosion, radiochemistry, electrochemistry, supermedical chemistry, and possess unique experimental facilities. So these are possible collaborations with our group and all the institution. We are open to new collaborations in various fundamental and comprehensive tasks. Thank you for your attention.
Thank you so much, sir. Well, moving to next, we're going to be having the next presentation is from Ermokin Sigurgi. He's from LIT State Technical University, named after II Pozanov, Russia. Is he available? So yes, we're going to be moving further, and the next topic is going to be delivered by Navrukbez Mirza Alimo from Andijan State University, Uzbekistan. Is he available? All right, so I think it's time to have the preceding part done, and here I'll be requesting Professor B.K. Panigrahi to please present his remarks.
Okay, very good evening to all of you. Is it audible?
Yes, sir, you're audible.
Okay. So I must thank all the participants who have taken the pain to present their findings, their innovations in this particular theme of sustainable energy and storage. So as categorically mentioned in my topic, but my topic was a little bit ahead of the utilization of this renewable energy and storage. So most of the deliberation which have been done today is based on the very fundamental science related to the storage, the technology, the materials, and all these things. So the first presentation by Dr. Lu is quite impressive, as she has categorically pointed out about not developing the technology, but looking into the technology, how it can reach to the market. So mostly it depends on the market players. Whenever we are developing some technology, we have to bring this technology into TRL 7 or TRL 8 technology transfer level. So at that level only we can implement it, or it can go to the industry or practical demonstration. So that's most important. So any development, any technology we are doing in the lab as researchers, and my young scientists have developed anything. So having an ultimate aim, how it can be utilized in industry or in any of the flora. Similarly, her idea about the jointly constructs to R&D platform is quite impressive. The second topic, which is presented by Dr. Lehe, particularly the photocatalytic CO2 hydrogen economy. Hydrogen economy is most of the important thing nowadays. because we can utilize it for our electric vehicle approach or other approach, as particularly the last speaker, Ilham and Scope, have told categorically the storage, hydrogen, methanol, and he has nicely shown about the use of this hydrogen in the vehicle. So we can utilize it for the hybrid electric vehicle. The other presentation by Haipeng Li particularly focused on the IoT, the energy, low consumption energy of the IoT, because IoT platform is a must for the energy sector, for the storage sector, for the monitoring, for the control, for the diagnostics also. So that's a very nice idea for developing various energy harvesting tools, techniques, the chips, or anything which is presented by Haipeng Li. Coming to the presentation by Dr. Joshi, that is most important thing, the CO2 reduction and perovskite material, which is the need for the solar thin film. Because initially, when you have opted for this renewable energy in the form of solar, I remember in India, the cost per unit was more than 14 rupees or 15 rupees INR. It is only because of the material. So there are a lot of development in the material, the solar material. So I hope nowadays the researchers are looking into various material so that the cost can be further reduced. So that is one of the challenge, and Dr. Joshi has categorically presented this. The most important presentation also by Dr. Saurabh, that is related to the agricultural waste, which is one of the major problem in northern part of India. Maybe everybody is looking into. So the pollution, the agricultural waste. So it is nice the young researchers have to come up with some solutions so that we can reduce this particular the pollution created from the agricultural waste. Dr. Jadasankar also presented about perovskite nanoparticles. Dr. Alexander categorically told about nitrous oxide and everything. So on the whole presentations are quite informative, and some can be taken to the market. So this nice presentation. I thank all of you. I thank the organizer and particularly the host to take care of the time. She has already arrived. So I hope my time is over. Thank you.
Thank you so much, sir. It means a lot. Well, thank you so much, everyone, for taking out time from your busy schedules, coming down and marking the spectacular gathering with the glory of your presence. So tomorrow, the first thing which we're going to be doing is a thematic networking and group discussion on future perception, which will be starting sharp at 10:30. So yes, make sure that you're available on time. So see you all soon. Till then, thank you so much. Have a great day ahead. Enjoy yourselves to the core of your hearts. Thank you. It's day 2 over, and day 3 we're going to be welcoming you again. Thank you.
Thank you. Thank you. Bye.